Welcome to this explainer. When we look up at the night sky, we generally just see a vast, silent emptiness. But right now, literally crisscrossing through that dark void are these invisible threads of data. It's this incredibly complex web of signals connecting us to all our robotic explorers scattered across the solar system. This is the NASA Deep Space Network, or the DSN. Managed by the Jet Propulsion Laboratory, it is absolutely the ultimate invisible lifeline for interplanetary exploration. And frankly, it's the most sensitive telecommunications system in the entire world.
But let's ground this with a really practical question. How do you actually download a picture from Jupiter? Just think about your everyday internet use here on Earth for a second. If your Wi-Fi router is just in the next room, you still might get a blurry video, right? Now imagine trying to catch a signal from a spacecraft that is hundreds of millions or even billions of miles away. We're not talking about a booming broadcast here. It's practically a whisper from the cosmos.
So, to even hear that whisper, you need some seriously heavy-duty infrastructure. According to JPL, once a spacecraft reaches an altitude of 30,000 kilometers from Earth, which, to put that into perspective, is roughly 3 times the diameter of the Earth itself, it has effectively left our immediate neighborhood. At this staggering distance, the spacecraft is always in the field of view of at least one of NASA's massive tracking stations here on the ground. But honestly, that's really just the starting line.
So what even counts as deep space? Well, the International Telecommunication Union sets aside very specific frequency bands for this stuff, and they define deep space as starting at a massive 2 million kilometers, or about 1.2 million miles, straight up from the Earth's surface. Think about that for a second. That means missions to the moon or even the James Webb Space Telescope are technically considered near space by these specific telecommunication standards. It really puts the mind-bending scope of this network into perspective.
And this brings us to a huge, fundamental engineering difference. Say you're tracking a satellite in low Earth orbit, like the International Space Station. That satellite is zipping overhead incredibly fast and is only visible for very short bursts of time. So you need a ton of stations all over the globe just to constantly hand off the signal. Deep space tracking is the exact opposite. Because the spacecraft is so incredibly far away, it's visible for long, long periods of time from a massive portion of the Earth's surface. You only need a few stations, sure, but they have to be equipped with absolutely massive antennas, crazy powerful transmitters, and ultra-sensitive receivers just to bridge that vast empty distance. Section 1. 3 stations, 1 Earth, a network that never sleeps.
Okay, so because the Earth is constantly rotating, a single massive antenna would eventually turn its back on a distant spacecraft. You'd lose the signal every single day. NASA obviously needed a global solution, so they built 3 primary facilities, spaced roughly 120 degrees apart around the globe. We've got the Goldstone Complex in California, the Madrid Complex in Spain, and the Cambria Complex down in Australia. Because of this setup, as the Earth turns, a spacecraft setting on the horizon in California is simultaneously rising on the horizon in Australia, which permits constant, uninterrupted observation. And if you look at the geography, it's super intentional. These facilities are built in semi-mountainous, bowl-shaped terrain. That natural physical shielding protects those ultra-sensitive receivers from all the everyday radio frequency interference bouncing around here on Earth.
Now, this incredible network didn't just appear overnight. Its roots go all the way back to 1958. This was actually before NASA was even officially formed, back when JPL deployed these portable tracking stations for America's first satellite, Explorer 1. Fast forward to 1969, and the DSN was playing a totally crucial supporting role for the Apollo moon landings. By 1989, they were pioneering this amazing technique of linking antennas together just to catch the incredibly faint signals from Voyager 2 out at Neptune. And today, spanning a timeline all the way into the 2020s, the network is undergoing massive upgrades to prep for humanity's return to the moon under the Artemis program.
Section 2. Science and Spacecraft Survival, the highest stakes in the solar system.
You have to realize the Deep Space Network is not just some high-tech telephone line. It's a critical lifeline for both groundbreaking science and literal spacecraft emergencies. A historical NASA report actually notes that while a separate network handled the day-to-day Apollo communications, the DSN stepped in with its much larger antennas for the really critical moments. The most famous example, they provided the emergency communications during the Apollo 13 crisis. When every single ounce of power on that crippled spacecraft had to be conserved, it was the raw size and extreme sensitivity of the DSN's antennas here on Earth that managed to catch the astronauts' incredibly faint signals. It acted as a literal lifeline to help bring them home safely. But beyond survival, the DSN actually performs international scientific experiments itself through radio astronomy. Take the Juno mission that's currently hanging out at Jupiter. The DSN beams a very specific Ka-band radio signal up to Juno. The spacecraft receives it, processes it through a special piece of hardware called a Ka-TS box, and then beams a brand new signal right back to Earth. By measuring exactly how that radio signal shifts over that massive round-trip journey, scientists can determine the velocity of the spacecraft with such extreme precision that they can actually map Jupiter's gravity field. The network itself is literally the scientific instrument.
Section 3. The Deep Space Traffic Jam, when the universe gets crowded. As magical as all of this sounds, we are currently facing a massive, totally unprecedented problem. The solar system is getting crowded. A 2023 audit by NASA's Office of Inspector General laid the reality completely bare. The DSN is currently oversubscribed. There are simply too many missions out there and just not enough antenna time to go around. This capacity limitation is already leading to scheduling nightmares, it's forcing mission planners to literally fight for bandwidth, and it's occasionally even impacting the scientific return of various missions.
Understanding the technical bottleneck here is really crucial. Engineers cleverly developed a system called Multiple Spacecraft Per Aperture, or MSPA. Basically, if several spacecraft are clustered together in the sky, say a bunch of orbiters and rovers all hanging around Mars, one giant antenna on Earth can listen to up to 4 of them at the exact same time. But because of the massive physics involved, we can only talk back or uplink to one spacecraft at a time. It's kind of like trying to talk over a loud crowd at a party, right? You might be able to hear 4 people talking to you at once, but if you start shouting back at everyone simultaneously, the interference totally drowns out the faint voices you're trying to listen to. So, we can listen to 4, but we can only speak to 1.
And the challenges compound from there in a way that's almost absurd when you think about it. On one hand, we've got these legacy missions, like the historic Voyager probes, operating decades past their original lifespans. They are so incredibly far away, they absolutely require the largest antennas we have just to hear them. But at the exact same time, those massive 70-meter antennas are aging, and they require maintenance that takes them completely offline for months at a time. Add in the inherent data rate constraints of communicating across billions of miles, and the looming surge in demand from the futuristic, crewed Artemis missions to the moon, and you can easily see why this global system is under such incredible strain right now.
Section 4. Upgrading for the Artemis era, expanding the interplanetary internet. Fortunately, NASA is definitely not just sitting still. They are actively modernizing. The absolute backbone of the DSN has historically been the gigantic 70-meter antennas. I mean, these are dishes that are literally the size of a football field. But as we just talked about, they're aging, and they are really tough to maintain. So NASA's solution is a major pivot toward modern 34-meter beam waveguide antennas. While the old 70-meter Titans are undergoing these intense, decades-long refurbishments just to keep them alive, NASA is aggressively building out these new 34-meter dishes, aiming for a total of 4 at each global complex.
Now, you might be wondering, why build smaller dishes if we need more power? Well, it's because of a really brilliant technique called arraying. By electronically linking 2, 3, or even 4 of these 34-meter antennas together, they can perfectly mimic the raw receiving power of one giant 70-meter dish. They can even link them across continents, combining a dish in California with one in Australia. This gives the network incredible flexibility. If one 34-meter dish needs maintenance, the others just keep working, which completely eliminates the single point of failure that we had with the older, massive dishes. So, looking at the big picture of how we're going to solve this capacity crisis, first, we keep the old 70-meter workhorses alive through deep refurbishment while building out arrays of the new 34-meter dishes. Second, NASA is creating entirely new lunar exploration ground sites. This is going to be a completely separate network that will handle the heavy traffic of the Artemis moon missions, freeing up the DSN to focus strictly on deep space. And finally, and this is the part that is incredibly exciting, they are prototyping optical deep space communications. That means using lasers instead of radio waves. While they are a bit susceptible to weather here on Earth, lasers could offer vastly greater communication speeds, totally revolutionizing how much data we can actually pull down from the solar system. Which really leaves us with this final thought. The Deep Space Network is totally the unsung hero of space exploration. Without it, our probes are literally just silent metal boxes floating in the dark. But as our ambitions grow, as we set our sights on crewed missions to Mars and robotic explorers heading to the ice moons of Jupiter and Saturn, the data demands are only going to skyrocket. The DSN is adapting today, but as humanity pushes further into the cosmos, How will we build the interplanetary internet of tomorrow? Is it going to be lasers, orbital relays stationed at Mars, or maybe something we haven't even thought of yet? I really hope this explainer gave you a deep appreciation for the invisible threads connecting us to the stars. Keep wondering, keep learning, and I'll catch you next time.